This conference will now be recorded.
Hello everyone. So we'll start with a problem, and this problem we will solve based on whatever we have learned in the last class. So last class we have already started electron displacement effect, and there we have covered resonance, then inductive effect, and also electromagnetic effect. One effect is left, which is hyperconjugation. That we will start today, and after that we will start reactive, intermediate, and related problems. Here we have this problem which is saying that the correct order of C double bond O bond length in these three species. So the first species is ethyl propanoate. Okay. Here pictures are already given for these three molecules, but even if it is not given, then also you can draw it from the names. So ethyl propanoate. So this part is ethyl and propanoate. Why? Because we have total 3 carbons. So this is a start. Then we have ethyl propenoate, which is the second compound. Now it is just like the first one, only difference is now it is propenoate, not propa, because we have CC double bond here. And the last one is ethynyl propanoate, because now instead of simple ethyl group, we have CC double bond in the right hand side. So that is why it is not simply ethyl, it is ethynyl. Okay, so also though these are not required to solve the problem, but still I am discussing it so that you can get some idea how from the nomenclature you can also draw the structure in case the structures are not given. Now correct order of CO bond length. So it is indirectly asking in which case maximum amount of resonance will take place, because when resonance is very high, that means C double bond O. Suppose there is C double bond O, and in any of these side there is some CC double bond. So if CC double bond is present, this type of resonance will occur, and this will increase resonance, and after resonance you will see the double bond character of this is now lost, and here positive charge will be, sorry, there is double bond not here, the double bond will be now in this position, and here we will have positive charge. But in this case one thing is clear, that when resonance is high, then the bond length will also increase. So bond length of C double bond O, that will also increase when resonance is very high, and if resonance is low, that means C double bond O character is also intact, it is not disturbed. Now another way also resonance can occur for carbonyl, that is C double bond O group. If you have some heteroatom like oxygen or nitrogen, then this lone pair can also take part in resonance, and as a result now double bond character is lost, and now we will have C double bond in the other side. But in this case also, from the double bond character now you have some single bond character. So that is why when resonance is very high, bond length will also increase. So we have to find in these three compounds in which case resonance is high, because when resonance is high, that means in that particular compound C double bond or bond length will also be high. Now here if we see the first compound, here we have this lone pair in the right hand side, and this type of resonance is possible. And for the middle compound, both side resonance is possible. That means this side resonance is possible. You can also do it from the other side because of this lone pair over oxygen. That means in this case resonance amount is high compared to 1. So 2 must be greater than 1. Now what about the last one? In the last one it is interesting because this lone pair which is present on this oxygen, this can undergo resonance to this side. Fine. And it is this can also take place on the left hand side. Now when you are following the blue arrow, then only this C double bond O, this double bond character is decreasing. But remember this lone pair, it is also engaged in resonance with another CC double bond. That means the chance that this lone pair will take part in resonance with this C double bond O in which we are interested, because we just want to know the C double bond O, that amount will decrease. So minimum amount of resonance will occur in case of 3 and maximum will occur in case of 2, and 1 is something in between. That means maximum CO bond length you will find in case of 2, after that it is 1, and then it is 3. and it is matching with the last option. Clear? So this is the way we have to solve this problem. Now one effect we have left, which is hyperconjugation, and that is under the heading of electron displacement effect in covalent bonds. This is number 4. We have already finished 3 effects, right? Inductive effect, electromagnetic effect, and resonance. These 3 we have finished. Now this is number 4 left under this heading, electron displacement. Now hyperconjugation, it is also known as no bond resonance. So you can say it is a kind of resonance, but it is not like resonance. It is no bond resonance. It is also known as Baker-Nathan effect. And this effect is permanent effect. You have seen in case of inductive effect that is a permanent, but electromagnetic is not permanent. Just like inductive effect, here also the effect is permanent. So what happens in this case, if you look at this right hand side picture, here we have ethyl carbocation. Ethyl carbocation means CH3, CH2 plus. So here you can see this is CH3 and then CH2 plus. Now with respect to this positive charge, that is carbocation, this carbon is just beside it, which is alpha carbon. That means with alpha carbon you have 3 hydrogen. So these 3 hydrogens are known as alpha hydrogen. So here you can say total 3 alpha hydrogens are present. Now this alpha hydrogen, if you consider these sigma bonds, total 3 sigma bonds are there. Now the electrons that is present in the sigma bond, that will be stabilizing the vacant p orbital of this carbocation. So this is positive charge over carbon. Actually, what is carbocation? That is a type of reactive intermediate. Details of carbocation we will deal with later. Probably in today's class we will be able to do so. But right now just remember, here this carbon is not fully satisfied. Here you have only 3 bonds. Normally carbon should have 4 bonds, but you have only 3 bonds. That means 1 bond is less. And 1 vacant p orbital is present in case of carbocation. Now when there is vacant p orbital is present and these sigma electrons, this carbon hydrogen sigma bond, electrons are present. So these electrons are basically stabilizing this vacant p orbital. And now when it is stabilizing, what happens? Ultimately these CH bonds are broken. And as it is broken, that is why it is also known as no bond resonance. Now the same thing you can also have for the other 2 hydrogens. So that is why the more is the number of alpha hydrogen, more will be the hyperconjugation effect. Fine. Now what will happen if I completely break this carbon hydrogen? So see, if I am breaking this carbon hydrogen, that is I am breaking this bond. Now what will happen? There will be CC double bond. So these 2 electrons that are present here, now it will form bond with the carbon over which initially we have some positive charge. Now the hydrogen, that is this bond is broken. So now this H, that will remain as H plus, because we have already broken the carbon hydrogen bond and we have now the electrons that are originally present in the carbon hydrogen bond. Now they are present here. So this H, it is devoid of electron, that is why it is H plus. So in this way you can draw the hyperconjugation. That is what will happen after hyperconjugation. So as the bond is broken, so that is it is also called no bond resonance. Now in this example you are seeing this with some carbocation, but it is also possible if you have some CC double bond, that is if you have some unsaturation present just beside this CH3. So I am taking here, suppose instead of writing CH2, if I am writing here H2C double bond, then C, H and CH3. Now this CH3, the 3 hydrogens that you are seeing here, all these are alpha hydrogen with respect to this carbon, right? Now these electrons, it can also take part, that is it can also interact with these pi electrons, okay? And as a result what will happen? Now if I am breaking this bond, it will make a bond at this position and this bond will be broken and negative charge will be over this carbon. Now the structure I am drawing, H2C, negative charge, single bond CH, double bond is here, CHH. And this H, it is present like this. So see, it is not just possible in case of a positive charge, but it is also possible if CC double bond, that is unsaturation, is present. Now look at this definition. It is a permanent effect in which delocalization of sigma electron of carbon hydrogen bond. So which sigma electrons? These sigma electrons, right? So these sigma electrons that are originally part of CH bond, or you can say CH bond of an alkyl group, when they are directly attached to an atom of unsaturated system. So that picture we have drawn here, this is an unsaturated system, right? Or it is attached to some vacant p orbital. That is possible with the carbocation. Then they generate extended molecular orbital. So now this original position of the electrons, now they are engaged up to this position. So the MO, that is molecular orbital, is as if now extended. Greater is the number of hyperconjugable hydrogen, which is nothing but alpha hydrogen with respect to carbocation, or you can say with respect to the unsaturated system. Greater will be the stabilization of that system or carbocation. Fine. So here are two examples we have seen. One more example we can consider, where again we will draw some carbocation. Now the carbocation is like this. Both sides we have CH3. Now if you consider this carbon which is carrying the positive charge, this position is alpha, this position is also alpha. That means how many alpha hydrogens you have? 3 alpha hydrogen here, 3 alpha hydrogen here. So total number of alpha hydrogen 6. So for this molecule you can draw 6 that is hyperconjugation structure, total 6 possible. Fine. Though they will be equivalent, but if you are numbering these 3 hydrogen separately, suppose if I am numbering these hydrogens as so I'm writing all the bonds extended way. Suppose this is 1, 2, 3, 4, 5, 6. So when you will be engaging, you will be breaking this bond, you will get one type of hyperconjugable structure like this. Now there will be double bond and carbon positive charge is removed. H1 is carrying some positive charge and this side we have not disturbed, so it is intact. Now the same type of equivalent hyperconjugation structure you can draw for the other 5 hydrogens. So total 6 hyperconjugable structures are possible. Now if I ask you that the original carbocation example, that is the first example in this slide, if you consider that is compared to this ethyl carbocation and this isopropyl carbocation, this is isopropyl carbocation Me2CH plus. In which case more stability is possible because of hyperconjugation? Obviously the answer is isopropyl carbocation. Why? Because now you have total 6 hyperconjugable hydrogens. But in the original example you have total 3 hyperconjugable hydrogens. Don't think these two are hyperconjugable hydrogens, because this is not, these hydrogens are directly attached to the carbon. But we have to consider alpha hydrogen, the hydrogens attached to the alpha carbon. Okay, so not these two hydrogen can take part, but this one. So ethyl carbocation, that will be less stable compared to this one because of higher number of hyperconjugable hydrogens. Fine. Now we will solve this problem that is based on hyperconjugation. It is asking that out of these 4 molecules, in which case hyperconjugation will be possible. Now what is the common point that you can see in these 4 molecules? Obviously you have some CC double bond, right? So in all cases you have CC double bond. Now hyperconjugable possible. What is the meaning of this statement? The meaning is there must be presence of alpha hydrogen. If there is no presence of alpha hydrogen, how hyperconjugation is possible? It is not possible. So with respect to this CC double bond, you just have to find You just have to find first the alpha position. So with respect to the first CC, this is the alpha position. With this, we have total 3 deuterium. Deuterium is also okay. It is just like hydrogen. So you can consider it as if it is hyperconjugable hydrogen. It is just isotope. Left hand side, we don't have any alpha carbon. Then that is with respect to this system, there is no alpha carbon. Then for the molecule B, this is the alpha carbon. Molecule C, this is the alpha carbon. Molecule D, 2 alpha carbon. Now look at the alpha carbons. Is there any hyperconjugable hydrogens? For the first case, we have total 3D deuterium atom, right? But in case of B, this carbon, there is no hydrogen, right? In C molecule also, there is no hydrogen because it is benzene ring. There will be some double bonds, like if you remove this circle sign, so there is also no hydrogen. And this carbon, there is also no hydrogen. So in these 3 cases, hyperconjugation is not possible. Only possible for the first one. And for the first one, how it will be? Let me draw it. See if I am writing all the deuterium like this. Now, so what type of structure you are getting? Now there will be negative charge here. When it is carbocation and you are doing some hyperconjugation, obviously no negative charge will be generated because there is already some positive charge, right? But here, as it is neutral molecule, there will be negative charge, newly generated CC bond. Deuterium is now with positive charge because this bond is already broken, and 2 deuterium still there. 2 more hyperconjugation, that is for these 2 are also possible. But the point is here hyperconjugation is possible only in the first molecule, not the other 3. Hyperconjugation involves overlapping of the following orbitals. So out of these 4, you have to choose the correct one. So it is not pi-pi. Remember the structure H2C plus then CH3. So here what we have done, here we have vacant p orbital, and these sigma electrons basically can take part in reaction, in bond formation with this vacant p orbital. So it is the interaction between sigma electrons and another vacant p orbital. So it is not pi-pi, not this one, sorry, this is pp orbital, this is pi-pi, this is sigma-sigma, and this is sigma p. That will be actually the correct option. Fine. Now come to the second question. The stability of 2,3-dimethyl butene is more than 2-butene. This can be explained in terms of what? Here total 4 different terms are given. All are electron displacement effect. But first of all, you have to draw the structure. So this molecule is butene. That means we have total 4 carbon, 2 position there is in 1, 2, 3, 4. And at 2 and 3 position, we also have 2 methyl groups. So this is the structure, and 2-butene means simply like this. Now the first molecule is more stable. Why? That is the question. So in this double bond, you have 2 hydrogen and 2 methyl groups. But in the previous molecule, you have total 4 methyl groups. Now 4 methyl groups means with respect to CC double bond, all this carbon is basically alpha carbon. And with each alpha carbon, you have 3 hydrogens. And all these 3 hydrogens are basically alpha hydrogen. If I am drawing the structure fully, it will be like this. So all these hydrogens, in total 4 methyl groups, all are basically alpha hydrogens. So 3 into 4, total 12 alpha hydrogens you have. So these are hyperconjugable hydrogens. But in case of 2-butene, you have only 2 methyl group to total 6 alpha hydrogen. So because of higher number of alpha hydrogen, it will be more stable. And that is because of hyperconjugation. It has nothing to do with electromagnetic effect. Because in electromagnetic effect, you have to use some outside reagent that you are not using here. And inductive effect, that is only for sigma bond. So these 2 you can cancel. And resonance is possible when there will be at least 1 double bond with another double bond or with another lone pair or negative charge. That also we don't have it. Only option left is hyperconjugation. So the stability, the driving force here is why it is more stable. Actual reason is hyperconjugation. So sorry, please. Okay. So next we will start after hyperconjugation reactive intermediate, and under reactive intermediate the first we will start with carbocation. You have already seen the carbocation in the when we have discussed hyperconjugation, but now we will discuss it in detail. So first of all, if there is a question arising in our mind that what is reactive intermediate, we have already seen in previous classes what is the meaning of intermediate. It is something which is produced before the product. So suppose you are starting with a reaction from A and your product is B. So sometimes intermediate, that is before the production of the final product B, there is some intermediate I generated which is not the final product, but it has some amount of stability. Otherwise, how it will be, we will be able to characterize it. There is some amount of stability, though that varies. After all, they are reactive intermediate, so you cannot expect very high stability. They are very reactive, and that is why ultimately they are converted to the final product B. But still, compared to transition state, their stability is high. So what is transition state? What is intermediate? Everything we have already discussed in one of the previous classes. Now, this reactive intermediate, we will go into the details. Different types of reactive intermediates are there. Mostly you will see they are carrying some positive charge or negative charge. So we are starting with that with that reactive intermediate which is carrying positive charge, and positive charge obviously on carbon, because this is organic chemistry, so mostly carbon based compounds will be there. So this intermediate is positive charge over carbon. Now, as a definition for carbocation, it is true there is positive charge over carbon, but there is some other features that we have to know related to carbocation. It is trivalent. Okay, so trivalent means unlike normal, that is neutral carbon, where we know valence is 4, total 4 bonds will be there, but in this case it is trivalent. Okay, bearing obviously a positive charge, and total number of electrons surrounding this carbon in the valence shell is only 6. Because if you consider normal carbon where 4 bonds are present, that is neutral carbon I am talking about. So all these 4 bonds, there will be total 8 electrons surrounding carbon, but now there will be only 6. Why? Because now one of the bond is not present, instead there is some positive charge. So total number of electrons surrounding carbon is only 6. Now, how it is formed? These are formed by heterolytic cleavage. Remember, we have already learned what is homolysis, what is heterolysis. Heterolysis means when you are breaking a bond, suppose you are breaking the bond between two atoms, M and N, you are breaking, then positive charge will be over one atom, negative charge will be over another atom. And if it is homolysis, then it will be M carrying 1 electron, N carrying 1 electron. But that is homolysis. We are talking about heterolysis, where both the electrons will come to one atom. Another atom will be completely devoid of electron. So these are formed by heterolytic cleavage of covalent bonds, in which leaving group takes away the shared pair of electrons present in the bond broken. What is the meaning of this? That you can see here. So initially in the right hand side, we have carbon bromine bond, and rest of the 3 valence that is satisfied by some R group. It may be semi-alkyl group. Simply you can consider hydrogen or methyl. So this is tetrahedral. We know when carbon is having 4 bonds, it is sp3 hybridized, it is tetrahedral. So this is a bromoalkane, because alkane means carbon hydrogen, and when you have replaced one carbon hydrogen with bromine, it will be called as bromoalkane. Now, if we are considering heterolysis of this bond, so initially when the bond is not fully broken, you can see some del plus charge, del negative charge, and this type of sign means partial separation of charge. Now, bromine is more electronegative, so obviously negative charge will be closer towards bromine, right? And when the bond will be fully broken, bromine will take both the electron with it. It will be now bromide ion. What will be the fate of carbon? Now carbon is converted to planar structure. Okay, so you can see if you join these three positions, you will get as if a plane which is perpendicular to the screen, and this p orbital is also perpendicular to the plane, this diagonal plane. Okay, and now the carbon, its hybridization is also changed from sp3, now it is sp2. So hybridization of carbon is sp2 for most of the carbocations. Only in some cases it is sp, in which case, in case of vinylic and aryl. Now what it means, that we will discuss in the next slide under the heading of types of carbocation. But remember, mostly it is sp2 hybridized when you have no double bond attached to this carbon. Here you can see all are simply sigma bond. So when you have simply sigma bond like this, it will be trigonal plane. Now sp2 hybridization, how we can understand it? We know under normal condition, carbon is having 2s2 2p2 configuration, right? Now 2s2 2p2 configuration, total 4 electrons will be there. But now as when you are also considering electrons from the other atoms, so total electrons will be 8 under normal condition, right? But here I am talking about only the valence electron of carbon. So if we consider only the valence electron, this is 2s, this is 2p, right? So when it is excited state, it will be like this. But here 1 electron we will consider less because there is positive charge. Now when it is sp2 hybridization, there will be total 3 sp2 and 1 p orbital which is not part of hybridization. It is pure p orbital, and all these are sp2. So carbon will have this electron present in 3 sp2, and these 3 sp2 will form sigma bond with 3 R groups. It may be any group, hydrogen or methyl. So these electrons are now carbon is using for bond formation, and the pure p orbital, this is actually vacant, which is present perpendicular like this, as you can see here. So in this way you can explain the sp2 hybridization. Okay, so these 3 sp2 are used for 3 sigma bond formation, and the vacant p orbital is left. Though in case of vinylic and aryl, there will be sp hybridization, that we will also see. So see, its shape is trigonal plan, because this is trigonal and this is planar also. And as there is total 6 electrons in its valence shell, its octet is not complete. So that is the reason it can behave as electrophile. Remember in the last class when we have discussed about nucleophiles, electrophiles, under the heading of example of electrophile, positively charged electrophile, there you have already seen the example of CH3+, right? So now you can explain it why CH3+ will act as electrophile. Fine. Next we will see different types of carbocation. Here you can we have the most simple carbocation when all the substituents are hydrogen. So it is simplest, and it is called methyl carbocation. Now one H, if I replace with some alkyl group, it may be CH3, it may be ethyl group, propyl group, whatever, then it will be called primary, because now you have one carbon-carbon bond like this, because here also you have carbon. The second one is another hydrogen also replaced by some other alkyl group or same alkyl group. Two R1 may be same, may be different. Whatever it is, now you have only one CH bond, and this is called secondary. You can also use this type of sign. And tertiary means when you do not have any carbon hydrogen. So in all these cases, as there is 3 sigma bond, all these are basically sp2 hybridized. But sometimes what may happen, you will have some different types of carbocation. Now look at this one, it is called allylic. Now here the carbon which is carrying positive, it is still having 3 sigma bond. So this is also sp2, but there is also cc double bond, and this type of positive charge is very stable, as you can understand. because of resonance with the CC bond. This is allyl carbocation or allyl carbocation. This is stabilized because of this CC double bond. It can undergo resonance. What type of resonance? This will be the resonance. Now positive charge is here, CC double bond is here. So this type of resonance is possible. And this is also sp2 hybridized because with the positively charged carbon you have 3 sigma bond. Same explanation is also applicable for the last one, where you have benzene ring, then you have some CH2. Just consider benzene ring, and you have CH3. This is toluene. But if you have one carbon hydrogen bond broken, now there will be positive charge and it will be CH2. Now this is also stable because of resonance with the double bonds of benzene ring. But one point is clear: the carbon with which positive charge is present, there is also 3 sigma bond. So this is also sp2 hybridized. But the middle two, here we will have different type of hybridization. Because now the positive charge, if you look at focus on this carbon, this is part of CC double bond, isn't it? So that is why here hybridization, now it will change. Here you have 1 sigma, 1 sigma, 1 pi. 1 sigma, 1 sigma, 1 pi. Now for these two cases, the hybridization is sp. And how you will explain? So once there is sp hybridization, you will have 2 sp hybridized orbital and you will have 2 pure p orbital, which is unhybridized. Now the 2 sp orbital that will be used for sigma bond formation, right? And there is one electron present in pure p orbital that will be taking part in pi, because now we have 2 sigma 1 pi, and this is basically completely vacant, right? So as this is completely vacant, you will have the positive charge will be considered for this vacant p orbital. So for these two cases, that is vinylic and arylic, so this type of positive charge, vinylic is basically CH2 CH plus, and aryl means positive charge is directly present over the benzene ring. So it is as if you have benzene ring, you have 6 carbon hydrogen. But suppose if I am breaking one of the carbon hydrogen, there will be positive charge present. Fine. So here we have seen different types of carbocation along with their hybridization, how it will be. Next, we have to know the stability of carbocation. So for stability of carbocation, when you will decide, suppose a particular carbocation is given and you have to compare it with some other carbocation so that you can understand what is the stability order of different types of carbocation. Then which factors, based on which factors you will decide the stability of carbocation. These are the factors that you can see here. Neighboring carbon atoms. Now what it means by neighboring carbon atoms? Suppose you have positive charge. Just take the example of secondary. Suppose I am drawing a secondary carbocation where you have positive charge, one CH bond, another CH3. Now I am discussing it for the first effect, neighboring carbon. So these two are neighboring carbon for the with respect to C plus. Now in this neighboring carbon, you have alpha hydrogen, so total 6 alpha hydrogen. So that can take part in hyperconjugation, and hyperconjugation will give some stability to this positive charge, right? Another way also these two CH3 group will stabilize it because of its plus I effect. So by both inductive effect and also hyperconjugation, this type of neighboring carbon atoms are actually stabilizing the carbocation. Now the same thing if you compare with another carbocation where you have only one CH3 groups, not two. Now if I tell you, ask you which one is more stable, obviously the first one, because now you have only plus I effect only from one side and you have only 3 alpha hydrogen. So in this way, from neighboring carbon atom, we can understand whether which carbocation will be more stable. Now come to the next point. Neighboring carbon-carbon multiple bond. Now, if whether there is in the neighboring position there is CC multiple bond. Now that is possible with this allylic carbocation. So same allylic carbocation I am again a drawing. Now this CC bond which is present at neighboring position. Now don't think that in the second picture this is also neighboring. No, this is not neighboring. It is far from it. It will not be able to take part in resonance. Only in the first one will be take part in resonance. So in this way, if there is carbon-carbon multiple bond, it may be CC double bond or it may be a benzylic, where directly you have some benzene ring attached to the CH. So for benzylic and allylic, you can say that neighboring, because of neighboring carbon-carbon multiple bonds, that is CC double bonds, you can have this type of resonance, and that is the reason for its stability. The next point here we have neighboring atoms with lone pair. Now, neighboring atoms with lone pair, what it means? Suppose we have a CH2 groups, and this side we have, another side we have some alkyl group. I am not going into details, but the other side you have some OH group or you have some OCH3. In both cases, stability is possible. How? We know there is lone pair over oxygen or any O alkyl group. Now this lone pair can stabilize it. So it is donating electron to the CH2. You may think at a first glance that oxygen is electronegative. So it will draw electron by showing its minus I effect. Now I am not saying that logic is not possible. That logic is possible. Oxygen is electronegative. It can draw electron density and it will further destabilize the CH2 plus. But remember, this type of pulsar effect, this is more predominating compared to minus I. So ultimately, the effect of pulsar you have to give more significance. And what type of structure we will get after this type of donation? Now there will be CO double bond, but oxygen will be positively charged. So whenever you have some lone pair, neighboring atoms with lone pair, it is also possible with NH2. Suppose instead of writing OH, I am now writing NH2. Now also it can stabilize this positive charge because now we have neighboring atoms with lone pair. So it is possible with nitrogen, mostly oxygen and nitrogen, because even if you have sulfur, that effect will not be very good because sulfur is from third period, but nitrogen, oxygen both are from second period. So here this type of donation, proper matching will be there, proper matching of orbit. So it is mainly applicable for oxygen or nitrogen. Fine. Now only one point is left, which is aromaticity. Now sometimes if the positive charge, that is the carbocation, if the species is aromatic. Now how to decide aromatic? For that you have to consider these 4 points. The rules for aromaticity. First of all, the species has to be cyclic. Then there should be full conjugation. Then it should be planar and 4n plus 2 pi electrons must be present. If all these conditions are fulfilled, though details of aromaticity, the details of these 4 points we will discuss in the later half of this unit, not here. We will just try to finish it as fast as possible because here our purpose is not to discuss aromaticity. I am just discussing it because we are trying to see if the carbocation species is aromatic when these 4 conditions are fulfilled. Now how to understand these 4 conditions are fulfilled? I will take this example. Suppose we have positive charge over this cyclopropane ring and there is CC double bond. Now whether this species is aromatic or not, that you can decide. First of all, this is cyclic. This point is covered. It is full conjugation is present. Now full conjugation and simple conjugation, there is difference. Suppose if I am writing 2 CC double bonds and there is positive charge here. Now resonance conjugation is possible like this, but this part will not be able to take part in conjugation because this is sp3. Now conjugation that will be extended only up to this part. Now you cannot say it is fully conjugated. Full conjugation is possible in this example. So when you will have CC double bond here, now the positive charge is here. You can also draw some other resonance structures. Positive charge is here. So 3 resonance structures possible. So full conjugation is that factor is also fulfilled. It is planar. And 4n plus 2 pi electrons. Now what is the meaning of it? N may be any integer, n may be 0, 1, 2, like this. Here total number of pi electrons only 2. That means if you put n equal to 0, 4 into 0 plus 2, 2 pi electrons. So that factor is also fulfilled. So this species is basically aromatic because all these factors are complete here, and that is the reason this species will be very stable. Now if I am drawing another carbocation like this, where it is 5-membered ring with two, sorry, let me draw it clearly. This is 5-membered ring, positive charge is here. Now here also it is planar, it is cyclic, full conjugation is possible. So the conjugation structure, it will be like this. Now the positive charge is here. You can also draw the other resonance structures by shifting this double bond. Now the positive charge will be here. So conjugation is present, full conjugation present, it is cyclic, it is planar. But 4n plus 2 pi electrons rules are not satisfied because you have now total 4 pi electrons. And if you put n equal to 1, it will be 6 pi electrons. So after 2 pi electrons, next value for n equal to 1, it is 6. So it is not aromatic, it is not stable. Actually, it is anti-aromatic. When all these three conditions are fulfilled, but this condition is changed to 4n pi rather than 4n plus 2, now it will be anti-aromatic, and anti-aromatic species are very, very unstable. So in this way, you can understand when aromaticity factors is present, the species will be very stable. Now here you can see many carbocations with their stability order. Now this species, you are seeing something new, and this is at first position, even if it is more stable than pH3C+. This is pH3C+, right? Now I'll come to this point why it is maximum stable, because there is some special kind of stability present. But let me finish all this. It is pH3 plus, it is pH2CH plus. Now this is more stable because this positive charge can take part in resonance with the benzene rings, and total 3 benzene rings are there. But here you have only 2 benzene rings. Next you have positive charge, and here 3 methyl groups. Hyperconjugation is possible. Inductive effect is also possible. Now it is more stable than this benzylic, where resonance with the benzene ring is possible. So here hyperconjugation factor and inductive factor, these two are overcoming over this resonance. Next species is this one, allylic. Next we have secondary, only 2 methyl. Now these three, if you consider, though here arrow sign is like this, but their difference is not very high. They are more or less almost having same stability. Then this is primary, and this is simply methyl. Now I will come to this point why this type of species where some cyclopropane ring is attached to C+, they are very stable. Now I will take the simple one where we have only one cyclopropane ring attached, and there is positive charge. You can also replace these 2 hydrogen, you can attach 2 more cyclopropane, but I am just giving this discussing it with one cyclopropane. So what happens here? Normally we know when carbon is sp3 hybridized, the angle is 109 degree, right? But in this case, these angles are very small. Now when angle decreases, the P character of the hybridization, that is S is there, P is there. Just take sp3 hybridization. So here P character, it will be 75%, S character is 25%. Similarly, when it is sp, we know it is 50%, 50%. But P character basically increases when the angle is very small. See, for sp we know it is 180 degree. So see, when angle is increasing, basically S character is also increasing. Now here, though it is these three are sp3, but still because of this very low angle, P character will increase very much. Now P character increased, it means now though theoretically it is sp3, but actually it becomes closer to sp4. So when P character is increased, what happens? This electron density, now it will be like this. There will be out of this CC bond, and they will be somewhere present here. So as if there is pure p orbital present, it will behave like this. And this p orbital, it can stabilize the vacant p orbital. Sorry, it is actually vacant, so better I don't color them. So this will stabilize this p orbital, and it is also possible with this side. So as a result, what will happen, these sigma electrons, they will stabilize this vacant p orbital so much that ultimately this bond will be broken and it will make a double bond with this CH2, and positive charge will be present here. So this type of resonance, whatever you see, that is sometimes called sigma bond resonance, because sigma bond is involved. You can also say it is a special kind of hyperconjugation, because here the CC bond we have broken, because just like no bond resonance you have seen in case of hyperconjugation. And it is also sometimes called bent resonance. Sometimes it is also called dancing resonance. So these are the different terms used. So remember, whenever you have cyclopropyl ring attached to carbocation, the species become very stable because of this special kind of uh, resonance, right? So the angle is very small, that is a theoretical angle of sp3, it should be 109, but here the angle, because of this type of tight structure, cyclopropane ring, the angle is very small, it cannot attain 109. As a result, p character is very high, and as if there is pure p orbital present, and that can interact with this vacant p orbital. Ultimately, this CC bond is broken. We are getting this type of structure. Now we'll solve this and your idea of stability of order will be somewhat clear. So here the question, it is asking the increasing stability order of the following carbocation. See, this species we have just discussed, and P will be obviously more stable than R. And look at Q. This is interesting because it will be ultimately aromatic. Here we have total 3 double bonds. That means total 6 pi electron. So it is fulfilling 4n plus 2. If you put n value 1, 4 into 1 plus 2, 6. That means it is satisfying it. It is planar. It is actually it is not planar. What happens? Though details we will discuss later. I am not going here. This is not exactly aromatic. It is called quasi-aromatic, but still it is fulfilling all these criteria that we have just seen for aromaticity. It is fulfilling 4n plus 2. When n value is 1, it is also fulfilling the other criteria. Here resonance is also possible like this. So Q will be also stable because of aromaticity, but ultimately this P and Q, P will overcome everyone. So P will come at first position. So any of these two will be correct. Now after P, whether to choose R and Q. Though it is aromatic, but here you have total 3 pH groups. So you have to give some more priority to it. So 3 phenyl rings are there, and here we have only aromaticity. But we have to give more preference to this, because when some species becomes aromatic, it becomes very, very stable. And last position, we will have S. Now this is stable because it is just like allylic carbocation. And also after the resonance, when the double bond is here, you have positive charges here. There is some alkyl group which can also stabilize it by plus IF. So ultimately we are getting the result P first, then Q, then R and S. Okay. Again, similar type of question, which of the following is correct order of stability of carbocation? Now see, in the first case, we have total 3 cyclopropyl, and here we have only 2. Now when there is 3 cyclopropyl, that will be more stable compared to 3 phenyl, because 3 is pH 3, C plus. So 1 must be before 3. Okay. Now whether 2 is before 3 or not, now compared to 3 cyclopropyl ring, when you have only 2 cyclopropyl ring, the effect is to some extent less. So that is why now what happens, after 1 it will be 3, then it is 2, and at last position we have this 4. So 3 and 4, these two are stable because of some pH ring. 3 and 4 stable. Here we have 3 PhD, and in case of 4 we have 2 PhD. Okay, and 1 and 2, these two are stable because of cyclopropane. Here we have 2 cyclopropyl substituent, here we have 3 cyclopropyl substituent. In this case we have 2 cyclopropyl substituents. So 1 is more stable than 2 and 3 is more stable than 4. But when we are stuck between 3 and 2, you have to give priority because total 3 pH rings are there compared to 2 cyclopropyl. So that is why last option will be the correct option. Correct stability order of the following carbocations. Here CH2, so up to this point you will see all the 4 are similar. Everything is CH2, then CC double bond. Only difference is here you have methyl, here you have Me2 boron, then N-methyl and OM. Remember what we have learned how to decide stability order of carbocation. Neighboring carbon, multiple bond. So here we have neighboring carbon, multiple bond, but that is present in all the species. So you can't do anything based on that. Then you have to check whether there is any lone pair stabilization neighboring possible or not. It is true that here OMe, NMe, they are not directly attached to C+, but as there is some CC double bond, so ultimately resonance is possible. So what type of resonance is possible in case of last 2 species? So this lone pair, so in this way the double bond will be shifted and the structure that you get, it will be like this. Now the CC double bond is here, CH double bond OMe plus. Similar type of structure you can also draw here. NMe plus. Now in both cases this type of lone pair stabilization is possible. So which one you will give priority? You have to give priority to 3 because 3 here lone pair is over nitrogen, here lone pair is over oxygen. Now oxygen, because of its higher electronegativity, the tendency to give electron, and for nitrogen the tendency to give electron, if you compare, obviously nitrogen can easily give because of its lower electronegativity compared to oxygen. So 3 should come first. After 3 it should be 4. But what about 1 and 2? In case of 1, lone pair is not present here. But boron also there is lone pair. So what to do? How to compare? Remember, though in case of methyl, lone pair is not present, but this carbon, if you see, here it is having complete octet because total number of electrons surrounding this carbon is 8. In this side we have CH and then it is continuing. So octet is complete, but remember when it is boron, its octet is not complete. Here we have C, C. So total number of electrons only 6. So that is the reason BME2 it is basically electron deficient. And as a result, there will be a chance that this double bond, it can also be shifted towards this side to stabilize, to remove the electron deficiency of boron. So ultimately it is making the system more unstable even compared to 1. Because in 1 it is true there is no donating effect from CH3, but still it is not taking the electron from CC double bond, making the carbocation unstable. But that is present in case of second species. Okay. So 4 will be maximum, 3 will be maximum stable, after that 4, and 3 after 4. If you are sure about that, then also you can choose option C, because 3 and then 4, that you do not have in any other option, right? And even if you are stuck between 1 and 2, but if you are sure about 3 and 4, that 3 is more stable than 4, then also you can answer the question. So after 4 it will be 1 and then it will be 2. 2 is minimum stability. Again we have some 3 carbocations, correct order of stability. Try to understand this. This is CH2 and just beside it we have C double bond O. And this is electron withdrawing group. Resonance is not possible. Here resonance is possible. and the structure that you get after resonance. Now oxygen is positively charged. In this case, plus I effect is possible and hyperconjugation is also possible. It is ethyl carbocation. But as we know that resonance effect, you have to give a more priority. So 2 should be having more because of this resonance, which is predominating over these 2 effects. Plus R effect is present. So 2 will come first, then 3, and 1 will be minimum stable because here we have this electron withdrawing effect from the side of COCH3 group. So here C double bond O, the lone pair over this oxygen, it will not be able to show any plus R effect. Okay. So COCH3 as a whole, it is electron withdrawing group, and that is the reason it will have minimum stability. Fine. Okay, so one more problem is there, but we are at the end of the session. Okay, let me discuss it. In the following carbocation, hydrogen and CH3, that is hydrogen or methyl, that is most likely to migrate to the positively charged carbon. So this is positively charged carbon. Here you can see some hydrogen is there out, that is in the neighboring position. Here we have methyl also. Now migration, why it will take place? Migration can take place only if after migration you are getting some more stable positive, more stable species. Then only migration is possible. Now here it is mentioned CH3 at C4. Now if this CH3 is migrated to this, now positive charge will be generated here. Now this positive charge, it will be something like this. I am just focusing on this part. Okay. Now if it is hydrogen at C4, if this is migrating, then also you will get positive charge over this. There is C. If it is CH3 at C2, CH3 at C2, actually there is no C, yes, this one it is talking about. If this is shifted, now there will be a positive charge at this position. Okay. And if there is positive charge at this position after this migration, now here from this side there will be some positive plus I effect, and OH can also show plus R effect. Hydrogen at C2. Now if hydrogen at C2 is removed, now you will get positive charge here. It is already migrated, rest of the part no change. Now this will be maximum stable because here you have from both sides some plus I effect, and you also have plus R effect from OH. So when this H from C2 is migrated to the middle carbocation, and the new carbocation you are getting, that is actually more stable than the original carbocation. So you can also draw all this, though I have already drawn it. But in none of this structure, it is true there is some plus I effect from both sides, but it's none of this structure you have both plus I from both sides and as well as OH. Here also you have OH plus R effect, but plus I effect on, sorry, OH plus R effect, but you have plus I effect only from one side, not from this side possible. But in this case only, you have plus I effect from both sides. You also have hyperconjugation. You also have plus I. So that is why last option will be the correct option. Okay. So we'll end the session here. Thank you for listening.